Hi students. In this last video, we're going to talk about now that we understand how to determine if a bond within a molecule is polar or nonpolar. Now we're going to take that understanding and apply it to the entire molecule. So we won't look at just the bonds, we'll look at the entire molecule and whether it's polar or not. So just because a molecule has polar bonds doesn't mean that the molecule itself is polar. The degree of polarity in each bond, it depends whether or not the molecule's polar bonds cancel out. So if you've ever had physics or if you've ever taken pre-calc and you've drawn vectors, you kind of understand how vectors can cancel each other out. If you've never taken those, I wouldn't worry about it. I base everything on symmetry. So is CO2 a polar molecule? If you look at CO2, we've already discussed that the oxygen has an electronegativity of 3.5 and the carbon has an electronegativity difference of 2.5. So total difference is 1.0. This falls between the 0.4 and the 2.0, so this qualifies as a polar bond. But so does this. This is also a polar bond. And what we notice is both polar bonds have dipole moments with the same magnitude, and those dipoles end up canceling each other out. And you can kind of see this in this diagram that overall there's not one region that has a greater electron density. Now, what does this all mean? The polar bonds dipoles cancel out and give me a nonpolar molecule. This can be really confusing. So I just tell students, look, if you look at carbon, yeah, it has polar bonds attached to it, but both of the atoms attached to it are same atoms. So because these are the same atoms attached, it's symmetrical. And because carbon dioxide is symmetrical, symmetry means it's nonpolar. Doesn't matter that it has polar bonds. This is a symmetrical molecule and it's nonpolar. Now, does that mean that all linear molecules are nonpolar? No. This is a linear molecule. This is hydrocyanic acid. Carbon is the central atom and it has two atoms attached. So two electron groups, two atoms, linear molecule. Carbon is the central atom. It's the one furthest away from fluorine. And if I look at this, I have a polar bond. The polar bond is right here. Nitrogen is 3.0 electronegativity and carbon's 2.5. This is a slightly polar bond. So there is a dipole pulling towards the nitrogen. As a result, this has an overall net dipole. And you can look at it, this is a nonpolar bond, so I'm not going to worry between hydrogen and carbon. But the easiest way to recognize that this molecule is actually polar as a whole is it is asymmetrical. It lacks symmetry. So unlike CO2, where the two groups attached are identical, therefore it's symmetrical and nonpolar, the two groups here are not identical. Hydrogen and nitrogen are not the same. So as a result, this is not a symmetrical molecule and is polar. If I look at water, everybody knows water is polar. Why is it polar? It has two atoms attached to it, and they're both hydrogen. The key is this oxygen-hydrogen bond is polar, and there's a dipole going towards the oxygen. The reason why they're not canceling out is the hydrogens are not directly across from one another. so they're not canceling out. This is not a symmetrical molecule. We don't see it in this diagram because they're showing the molecular geometry of bent. But in actuality, if you drew the Lewis dot structure, you would see that there's two more electron groups of lone pairs. So what I tell students is you have 4 groups. Your electron geometry is tetrahedral. Your 4 groups are not the same. Because these 4 groups are not the same, 2 are lone pairs, 2 are atoms, this lacks symmetry. And because water lacks symmetry, it's polar and it has polar bonds. So how can we predict whether or not an entire molecule is polar? So first you got to draw the Lewis dot structure and look at the molecular geometry. The reason why you're looking at the molecular geometry is you want to make sure there's no lone pairs. If the bonds of the molecule are not polar, if they're non-polar bonds, then the molecule is going to be non-polar. So that's the first thing. Does the molecule have polar bonds or does it have non-polar bonds? Non-polar bonds, if all the bonds are non-polar, this is going to be a non-polar molecule. But if it does have polar bonds, you got to look to see if the dipole moments cancel out. And basically, it goes back to what I say. If the molecule has polar bonds and it's symmetrical, if they cancel out, if there's symmetry, then it's a non-polar molecule. Doesn't matter whether or not you have polar bonds. If there's symmetry, it's a non-polar molecule. If it's asymmetrical, like in the case of CO2, then we're going to, or I'm sorry, like in the CO2 was symmetrical. That's why it's non-polar. If it's asymmetrical, then you're going to have a polar molecule. So that's what's in the case of H2O. I hope that helps you kind of understand it. I always tell students, if it's symmetrical, it's non-polar. If it's asymmetrical, it's going to be polar, but you do have to have polar bonds to be polar. So look for that symmetry. Thanks for tuning in, and I hope that helps.